Okay, so here we are on page 65. We need to write ourselves a note. So the formula for a sum of cubes. So the way we would factor a to the third plus b to the third is going to be a plus b times a squared minus ab plus b squared. And the way we would factor a to the third minus b to the third is going to be a minus b times a squared plus ab plus b squared. So really, essentially, what you have to do is memorize these formulas, and then it's sort of just plug and chug from there. So if we look at example number 1, we've got a sum of cubes. So we're using this formula here. We've got x plus 5, since this is obviously x to the third. I won't even bother writing it. And 125 is 5 to the third. So we've got x plus 5 times x squared minus 5 times x plus 5 squared. Okay, if we try a difference, like in number 3, so we've got x to the third, and then 64 is 4 to the third, so we've got a difference of cubes. It's going to be x minus 4 times x squared plus 4x plus 16. Jumping down to number 7, it doesn't matter if your variables are reversed, so we'll just do it in the order that it's presented to us. So we've got 1 minus a times 1 plus a squared. And then for number 12, it helps to just rearrange it, so we can call this 125 minus 27u to the third, and now we've got a difference of cubes, this being 5 to the third and this being 3u all to the third. So we've got 5 minus 3u times 25 plus 5 times 3u, which is going to be 15u, plus 3u all squared, which is going to be 9u squared. And that's pretty much it. There's just lots more examples on the back. Okay, so next we've got factors and zeros. So we've done finding the zeros of quadratics. Now we're doing finding the zeros of higher degree polynomials. If we look at number 2, for instance, we just set it equal to 0, and now we have 3 possible solutions. We've got x equals 3, 3x plus 1 equals 0, so x is negative 1/3, or x equals negative 1. So that's the only difference. You're just going to get more solutions with higher degree polynomials. If you look at number 7, we've got 4 factors here, so we're going to get 4 solutions. Number 8, if you look here, you notice we have a linear factor and a quadratic factor. That quadratic factor is irreducible. So when we set that equal to 0, we are going to have to use the quadratic formula. So just a note there. Sometimes you will end up with quadratics that can't be factored down any further, and you will end up having to use either the quadratic formula or completing the square. Next, write a polynomial function of least degree with integral coefficients. This word integral, for those of you who have taken calculus, you've got the integral from a to b of f of x dx. That's an integral, sure, but integral also means integer. So if you have integral coefficients, that means your coefficients are integers. So that's another definition of that word, integral, in case you see it. Okay, so we want to write a polynomial function that has these zeros. So if x equals 3 is a 0, that means that x minus 3 equals 0 would be a factor. So we're going to have factors of x minus 3, x minus 2, and x minus negative 2, or x plus 2. And our original equation would look something like this once it was all factored. So all we have to do is really just multiply this all out and we'll get our polynomial function. So we've got x minus 3 times, this is a difference of squares, so this is going to be x squared minus 4, and then distribute that. We've got x to the third minus 4x minus 3x squared plus 12. Rearrange your terms in descending order if you want, and that's our f of x. Same thing here, right? If x equals 3 is a 0, then x minus 3 was the factor, x minus 1, x plus 2, and x plus 4. And again, you could multiply all of those out, and you would get a 4th degree polynomial, and that would be the polynomial of least degree, which is what we're asked. Certainly, you could add other factors if you wanted and get a polynomial of higher degree, and these will all still be solutions because these 3 factors were part of your longer polynomial. But if we're looking for least degree, then we just have to use each factor once. Okay. Next, find all zeros by factoring each function. So let's take a look at the first one. We can factor out an x. So we've got x squared minus 2x plus 1. This is this is a perfect square trinomial. So this is going to be x minus 1 all squared. So if we set this equal to 0, we're going to get x is equal to 0 or x is equal to 1. And remember, 0 has a multiplicity of 1, and 1 has a multiplicity of 2 because this factor is repeated twice. Okay, this is just a sum of cubes. You should be able to do that from the formula. Moving on to 17, this is a little trickier, but you can factor these into 2 pairs of factors as long as you've got a constant term at the end. So if you look at all of these, we've got a constant term at the end, and also the middle term. The middle term's degree is exactly half that of the first term's degree. So we've got a 4 and a 2, a 6 and a 3, 10 and 5. Anything where the middle term's degree is half of the first term's degree, and you've got a constant term at the end, will be factorable into 2 sets of parentheses as long as you've got the right coefficients. So what are we going to get here? We've got an x squared and an x squared. That's going to get us an x to the 4th out front, and an x squared is our middle term. And we'll have a minus 6 and a plus 5. So we want to set that equal to 0. Well, x plus 5 is never going to equal 0 because you would be solving x squared is equal to negative 5, and that has no real solutions. So that factors out. That factor is gone. So then we've got x squared minus 6. What I would do personally is well, you know what? No, I wouldn't. Well, actually, let me tell you what I would do, even though I don't recommend it. I would say this is x and x, a plus and a minus, because it's a difference of squares, and it's going to be root 6 and root 6. So either way, whether you did it like this and you broke it down into two factors, or you said to yourself, all right, I'm just going to solve x squared equals 6 and take the square root of both sides, which I realize now is the more efficient way to do it, even though my brain jumped to difference of squares. We end up with the same result, x is equal to plus or minus root 6. So those are our two zeros. Looking at number 20, we can do a similar thing here. So this is actually a perfect squared trinomial. So this is going to be x to the third plus 1 all squared. And if we set that equal to 0, we can take the square root of both sides. We've got x cubed plus 1 equals 0, x cubed equals minus 1, so x equals minus 1 because we take the cube root of both sides, remembering that we can take odd roots of negative numbers but not even ones. So x equals negative 1 is the solution to this. Okay, so the remainder theorem. What does the remainder theorem say? It says that, we'll put it right here, theorem. If f of a equals 0, then a is a root of f, i.e. x minus a is a factor of f. So this is a nice little theorem. Instead of having to do a bunch of polynomial division and seeing if this really is a factor, and when we divide, do we get something without a remainder, we can use the remainder theorem and we can just plug a value into the function and see whether or not this is going to be a factor. So let's do a few of these examples. So this wants us to evaluate at x equals 2. So f of 2 is going to be minus 2 to the third plus 6 times 2 minus 7. So we've got minus 8 plus 12 minus 7, and that gives us minus 3. So minus 3 is the remainder when we divide f of x by x minus 2. So we know that x minus 2 is not a factor of this function. Okay, let's try this one. So we're plugging in 2, f of 2. We got 2 to the third plus 2 squared minus 5 times 2 minus 6. That's going to give us 8 plus 4 minus 10 minus 6. So we've got, what, 12 minus 10 is 2, and 2 minus 6 is minus 4. Again, our remainder is not 0, so that means that x minus 2 is not a factor of this polynomial either. Okay, let's move down to one of these. Let's look at number 12. So we're dividing by n plus 5. So that means that we want to evaluate f of negative 5. Since negative 5, if n plus 5 is the factor, then n equals negative 5 is the solution. So we'll do f of negative 5. So that's going to be negative 5 to the fifth minus 25 times negative 5 to the third minus 7 times negative 5 squared minus 37 times negative 5 minus 18. this is somewhat atrocious, and I will be using a calculator. I advise you to take a minute and do the same. Okay, and my calculator gives me an answer of 202 if I typed in everything correctly. So that means that our answer is no. Since our remainder is not 0, this factor is, n plus 5 is not a factor of that polynomial. Okay, next. Let's do a little bit of polynomial long division once more. One more time through, just remembering the steps. So again, it's really important to make sure that you've got a coefficient for every single power of your variable, and if you don't, you need to fill in placeholder zeros. So that's very, very important. In something like example 26, you don't have a v to the third, or a v squared, and so you're going to need to fill in plus 0v to the third plus 0v squared when you're actually doing this division. So let's pick a short one that will probably fit on this page. Let's try number 21. So we've got a plus 4 on the outside, and we've got 6a to the third plus 20a squared minus 15a plus 9 on the inside. So we look at the leading term of each. A goes into 6a to the third, 6a squared times 6a squared times a is 6a to the third. You obviously want to have the same thing so that when you subtract it, it goes away. 6a squared times 4 is going to give us 24a squared. Subtract, subtract. That goes away. We've got minus 4a squared. We bring down the minus 15a. A goes into negative 4a squared, negative 4a times. We multiply through. We've got negative 4a squared, and then negative 4a times 4 is going to give us a negative 16a. Subtract, subtract, so that means these are going to become pluses. Those go away, and we're left with an a. We bring down the plus 9. A goes into a one time. 1 times a is a. 1 times 4 is 4. Subtract, subtract, and we've got a remainder of 5. So we would write this as plus 5 over a plus 4. And that's polynomial long division. Okay, moving on. Irrational and imaginary root theorems. So let's just take a look at what these theorems have to say. Basically, when we look at the highest degree of a polynomial, that's going to tell us how many total zeros it's going to have. Some of those zeros may be real, and some of them may be imaginary. So one thing to note, imaginary zeros always come in conjugate pairs. So, in other words, if 3 plus I is a 0, then 3 minus I is 2. So if you have imaginary solutions, you're always going to have an even number of them. So in something like this, this is going to have 2 zeros. So it has 2 complex zeros. And it could either have 2 real and 0 imaginary, or it could have 0 real and 2 imaginary. You can't have 1 and 1 because, again, imaginary roots always come in pairs. Same thing with this one. Since it's an even number, you're going to have 4 total zeros, so we say 4 complex zeros. You can have 0 real and 4 imaginary. You could have 2 real and 2 imaginary, or you could have 4 real and 0 imaginary. So those are our possibilities. With something that has an odd degree, you know that you're going to have at least 1 real root. Because if all of your imaginary, if you've had only imaginary roots, then you would have one missing its conjugate, and we can't have that. So you can have an even number of imaginary roots, and then there'll be 1 left over. So it has at least 1 real root, but the other 4 could be real as well. So this one, it's going to have 5 complex zeros. So let's actually start with the imaginary ones. So it could have 0 imaginary ones, meaning it would have 5 real. It could have 2 imaginary ones, so that means there would be 3 real solutions. It could have 4 imaginary ones, which means that there would be 1 real solution, and that's it. Those are our options. So that's how those, that is how those theorems work. Also, we know that when we have irrational roots, they also come in conjugate pairs. So if 2 plus root 5 is a 0 of your function, then 2 minus root 5 is also going to be a 0 of your function. So given that, let's try to find all the additional zeros if these are the zeros that we're given. So if we know that I is a 0, minus I is also going to have to be a 0. With negative 5, it doesn't necessarily need a conjugate, so it's fine by itself. Here, if negative 1 plus I is a 0, then negative 1 minus I is going to have to be a 0. And with root 5, if root 5 is a 0, then negative root 5 is also a 0. And number 9, if negative 3 plus root 5 is a 0, then negative 3 minus root 5 must be a 0. And if negative I is a 0, then positive I is also a 0. If we look at number 12, if 2 minus 2i is a 0, then 2 plus 2i must also be a 0. If 1 minus 2i is a 0, then 1 plus 2i is also a 0. The conjugate pair was given to us, so there's nothing else we need to do with that. All right. Next, write a polynomial function of least degree with integral coefficients that has the given zeros. So we know that if root 3 is a 0, minus root 3 must also be a 0. So we have to include that before we do anything. So we've got x minus 0 as a factor. I'm going to write it like that for now. X minus 2 x minus root 3 and x plus root 3. So these guys are going to be, these are a difference of squares. So this is x squared minus 3. And then this is just really x times x minus 2. So this is going to be x squared minus 2x. And then we can FOIL those. So we've got x to the 4th minus 3x squared minus 2x to the 3rd plus 6x. Let me just double check I did that right. Yep, that looks good. And so this is going to be our polynomial. And again, if you want to rearrange it so that it's in perfectly descending order, most professors would probably appreciate it. So I'm just going to leave it like that for right now. Okay, so let's do one with some imaginary solutions. So let's look at 18. We've got 2i minus 2i, that's good, that's a conjugate pair. We've got 2 plus 2i, so we're also going to need 2 minus 2i. Okay, so what have we got here for factors? We've got x minus 2i, x plus 2i. We've got x minus 2 plus 2i. And we've got x minus 2 minus 2i. So those second two look a little tricky. Let's work with them first. So this is x minus 2 minus 2i, and this is x minus 2 plus 2i. So all I did was I just distributed, right, those negative signs, and now I'm going to regroup. So I'm going to put the parentheses around x minus 2. So now we've got parentheses around x minus 2. We've got x minus 2 minus 2i and x minus 2 plus 2i. Now we've got a difference of squares, and we've got one here as well. So I'm just going to recopy this down. So what is this going to be? This is going to be x squared minus 2i squared, and I'm going to just leave it like that. And then this is going to be x minus 2 squared minus 2i squared. These problems get tedious sometimes. Okay, so what have we got? Well, we've got x squared minus 2 squared is 4, and I squared is negative 1. So this is negative 4 here. So we've got minus negative 4. So that's going to be a plus 4 in there. And then we've got this thing, which we need to expand, x squared minus 4x plus 4. And then again here, this is going to be minus 4, but with the negative sign out front, it's a plus 4. All right, we're getting there. So we've got x squared plus 4 times x squared minus 4x plus 8. And now we need to multiply all this out. Aren't we so lucky? Okay, so x to the 4th minus 4x to the 3rd plus 8x squared plus 4x squared minus 16x plus 32. And we can combine some like terms, so we end up with f of x equals x to the 4th minus 4x to the 3rd plus 12x squared minus 16x plus 32. And there we have it, a 4th degree polynomial with completely imaginary solutions. All right. So remember your conjugates. That's the moral of this story. And moving on. The rational root theorem. The rational root theorem says, suppose we have a polynomial p of x, and I'm going to write it from the constant term up to the highest degree. So we've got our constant term that's going to be a naught plus a1x plus a2x squared plus a3x to the third plus, and so on and so forth until we get to the nth one, however many there are. So this theorem says, given this polynomial, the rational roots are the ratio, all right, let's put the possible, because it might not necessarily have rational roots at all. It might just have irrational roots. So if it does have rational roots, these are the only things that it could be. So the possible rational roots are the ratio of factors of a naught to factors of a n. What does that mean exactly? I will show you in an example. So remember, we put our constant term first. So it's going to be, we're looking at a naught over a n. If we look at the factors here, the factors of -1, what are they? They're plus and minus 1. What about the factors of 3? Well, it's plus and minus 1, plus and minus 3. So the possible rational zeros are, we're going to take all combinations of the factors of these as fractions. So +1 over +1, +1 over -1, +1 over +3, +1 over -3. I'm gonna be really meticulous about this, so there will be repeated ones which we'll get rid of. But so I took +1 up here, and I combined it with all 4 options down here. I'm going to do the same thing with -1. So -1 over +1, -1 over -1, -1 over +3, -1 over -3. So really, we're going to get the same ones repeated, but I'm just being thorough. So these are all of the possibilities. So the possible rational zeros are 1, -1, +1/3, -1/3. So what if we did something like number 5? So let's start with the factors of -25 plus and minus 1 plus and minus 5 plus and minus 25. The factors of 4 plus and minus 1 plus and minus 2 plus and minus 4. So now I'm going to write it in a more condensed way. So what are our options? So we've got 1 over 1. So plus or minus 1. 1 over 2. Plus or minus a half. 1 over 4. Plus or minus a fourth. 5 over 1. Plus or minus 5. 5 over 2. Plus or minus 5 halves. Plus or minus 5 fourths. 25 over 1, so plus or minus 25, plus or minus 25 over 2, and plus or minus 25 over 4. So that's every single possible combination of numbers from here being the numerator and numbers from here being the denominator. And those are all of the possible rational roots. Again, it's only got 5 roots total, so maybe one of those, we know one of them has to be a real root, and possibly it is a rational root. And if it is a rational root, these are the only things that it could be. Okay, so let's look at number 9. State the possible rational zeros for each function and then find all of the rational zeros. So what we're going to do is we're going to use this rational root theorem, and we're going to use it in conjunction with the remainder theorem. So we've got 3 and 1 as so. Factors of 3 plus and minus 1 plus and minus 3, factors of 1 plus and minus 1. So our possible rational zeros are plus and minus 1 and plus and minus 3. So what we're going to do is we're going to evaluate. F of 1 is 1 plus 1 minus 5 plus 3, which is 0. So that's great. If f of 1 equals 0, that means x minus 1 is a factor. Okay, that's fabulous. So let's do a little something called synthetic division. So synthetic division will work as long as you're dividing by a very simple factor like x minus 1, x minus 4. Nothing too complicated, and especially nothing where you can factor out a number. So like 2x minus 4 would not be a very good candidate for this because you can factor out a 2 and that might mess up your solution. So something like this. So if f of 1 equals 0, then x minus 1 is a factor. X minus 1 is a pretty simple factor. So we can use synthetic division for this. So I'm going to do this over here. We're going to put a 1 outside since it's x minus 1. And then we're going to put the coefficients from f of x on the inside of the box. So we've got 1x to the third, 1x squared, negative 5x, and a positive 3. We drop down the first number and then we multiply. 1 times 1 is 1. We add 2. 2 times 1 is 2. Negative 5 plus 2 is negative 3. Negative 3 times 1 is negative 3. And lo and behold, we get a remainder of 0. So what do we get when we factor this? We've got x minus 1, and then what's left over is x squared plus 2x minus 3. That's great. Now we've got a quadratic, which is easily factorable. So we've got x minus 1, and we've also got x plus 3 and x minus 1. So x minus 1 has a multiplicity of 2, and x plus 3 has a multiplicity of 1. So our zeros are x equals 1 and x equals minus 3. So that's how you would do that. You would find your rational zeros, try to get those out of the way. You test out your rational zeros by plugging them into the function and using the remainder theorem. If you get 0 as a remainder, then you know that what you plugged in is a factor. And then you can use either synthetic division or polynomial long division and divide out that factor and get a smaller polynomial, and then try to keep factoring that. And then finally you'll get it down to where you can't reduce it any further, and you've factored everything as best you can. Okay, good. So let's now move on to evaluating functions. This should be pretty simple. So to evaluate a function just basically means plug in whatever they ask you to do. So for instance, h of 6 is going to be the absolute value of 6 plus 2 and then plus 3. So we've got 8 plus 3, and that's 11. It can get more complicated than that. So if we look at number 9, they're asking us to find p of t minus 2. So p of t minus 2 means that wherever we see t, we put t minus 2 instead. So it's 4 times t minus 2 minus 5. That's going to give us 4t minus 8 minus 5, or 4t minus 13. Same thing, let's look at number 16. So f of n squared is going to be n squared squared minus 2 times n squared. So we've got n to the 4th minus 2n squared. So that's pretty much it. Evaluating functions. Just be very careful with your algebra and make sure that you are careful in how you're plugging in whatever you're being asked to plug in. Okay, so on page 76, it's blank. I'd just like you to write in domain and range. So let's just do some quick definitions. So definition, the domain of a function is the set of possible x values. So note, anywhere you square root a negative or divide by 0 is out of the domain. And the range, oops, the range of a function is the set of possible y values. So for something like y equals x squared, the domain, we can use all real numbers to plug in for x, but if we look at the range, we know that it's always going to come out positive or non-negative. So we would say the range is y is greater than or equal to 0, or we could say from 0 to infinity, and likewise here, we could say from negative infinity to positive infinity. For something like the cube root of x, the y equals x cubed, the domain, it's all real numbers, and the range is also all real numbers. For something like the square root of x minus 1, the domain is x greater than or equal to 1, and the range is going to be y greater than or equal to 0. So just a little bit on domain and range there. Okay, finally, function operations. So one of the nice things about function operations is that they're pretty straightforward. So you multiply g times h, and then you plug in 1. So if we end up multiplying these two together, we're going to get negative 3n to the third minus 12n minus 6n squared plus 2n squared plus 8 plus 4n. So simplifying that a little bit, we've got negative 3n to the third minus 4n squared minus 8n plus 8. And now if we want to evaluate that at n equals 1, we're going to get negative 3 minus 4 minus 8 plus 8, which is going to give us negative 7. So first we need to multiply the functions, and then we substitute in our value. Here we would subtract the functions. So we've got 4x minus 3 minus x to the third plus 2x. So that's going to give us negative x to the third. We've got a 4x minus a 2x, so that's going to be plus 2x minus 3. And if we evaluate that at 4, we've got negative 4 to the third plus, well, let's see, what is that? That's negative 64 plus 8 minus 3. So it's going to be negative 56 minus 3 is negative 59. So same thing with adding. First you add them. Here you divide them. We would just have 3a plus 2 over 2a minus 4, just like that, and then you would plug in 3. So let's talk about composition of functions, which I believe we have on the back. Yes, we have a little bit. Okay. So h of g of x. So what we're going to do is we're going to take wherever we, in the formula for h, wherever we see x, we're going to plug in g of x. So h of g of x is going to be 4x plus 1 all squared, and then minus 2. So we've got 16x squared plus 8x plus 1 minus 2. So we end up with 16x squared plus 8x minus 1. If we look at the one down below, g of f of negative 2 plus x. So first of all, so that's g of f of negative 2 plus x. We have to figure out what is f of negative 2 plus x. So we've got negative 2 plus x all squared plus 3 times negative 2 plus x. Okay, so what's that going to give us? Well, we can rewrite this as x minus 2 squared plus, I'm just going to distribute this now. So this is going to be minus 6 plus 3x. So x squared plus 4x plus 4 minus 6 plus 3x. And we've got x squared plus 7x minus 2. Okay, that's just the first part. So now we have to do g of, so this is f of negative 2 plus x. Now we need to do g of that. So g of x squared plus 7x minus 2. So what's that going to be? That's going to be 2 times x squared plus 7x minus 2, and then minus 2. So we've got 2x squared plus 14x minus 4, and then a minus 2. So our final answer is going to be 2x squared plus 14x minus 6. Okay, so good. Those are all the pages that we didn't get to do, except for the things with complex numbers. So I'm just going to do that really fast. I think we kind of basically touched on most of it already. But just to make sure I'm being thorough. So operations with complex numbers, adding and subtracting is really easy. You just combine like terms. So for instance, number 5, -1 and -4 is -5. -8i minus I is -9i. So that should be pretty easy peasy. Here you would distribute as normal. Just remember, note I squared equals -1. That's literally the definition of I. So as long as you know that, you're fine. More of the same on the back. Okay, so moving on. Rationalizing imaginary denominators on page 59. So here what we're going to do is we're going to multiply by the conjugate. So in this case, if 8i is our imaginary number, -8i is its conjugate. So here we've got -16i on top, and on the bottom we've got -64i squared. So we've got -16i over -64 times -1. That's a positive 64. And I guess we could have reduced at the beginning, but I just realized that we could now. So we can reduce by 16. That's a 1 and that's a 4. So we've got -I over 4 as our final answer. Okay, let's do number 8. So we're going to multiply by a positive 6i, top and bottom, remembering that we have to distribute. So we've got -18i plus 60i squared all over -36i squared. So doing a little simplifying here, we've got -18i. I squared is -1, so this is going to be minus 60. And then this I squared is also -1, so that's going to be a positive 36 up there. 6 goes into everything, so we can factor out a 6 on top. So we've got -3i minus 10 all over 36. Cancel, cancel. And a final answer of -3i minus 10 all over 6. Okay. And then if we look at number 12, the conjugate of this is going to be -1 minus 3i. So we're going to have to distribute on the top, and we're going to have to FOIL on the bottom. Yay. So what have we got? We've got -8i minus 24i squared all over +1 plus 3i. Oh, this is a difference of squares, so we don't need to bother with that. Why am I doing all that? We don't need to FOIL. The whole point is it's a difference of squares. Okay, so let's try that again. -1 squared minus 3i squared. There we go. That's better. So on the top, we've got -8i, and then that's going to be a plus 24. On the bottom, we've got 1 minus. Well, that's going to be a 9, and that's going to be a -1, so we've got -9 on the inside here. So we've got minus -9, so that's going to be plus 9. So we've got 8i plus 24 all over 10. We can factor out a 2. So 4i plus 12 all over 10. Cancel, cancel. And final answer, 4i plus 12 all over 5. Okay, so that is rationalizing an imaginary denominator. And finally, properties of complex numbers. Okay, so find the absolute value of each complex number. Actually, before we do the absolute value, why don't we do graphing? So looking at number 11, graph each complex number in the plane. So we've got -3, that's our real part. and we've got a positive 4 on our imaginary. So this is where our complex number lives. Basically, it's at the point -3, 4. Okay, so if we want to look at the absolute value, it's basically the distance. So the way that the distance formula is calculated is by using the Pythagorean theorem. We know that if we travel a certain amount of x and then a certain amount of y, we've got two perpendicular sides, and then the hypotenuse is the straight line distance between the origin and the point that we're looking at. So we know that this is -3, this is +4, and this is a 3, 4, 5 triangle. If you didn't know that, then you could say that d, which is the distance, so d squared, let's say we don't know what this is, right? We'll call it d for distance. D squared is equal to -3 squared plus 4 squared. That's good old Pythagoras. So a squared plus b squared equals c squared, or in this case, d squared, because it's a distance. So we've got d squared is 9 plus 16, d squared is 25, so d equals plus or minus 5, but since d is a distance in this case, then we're only using the positive value because distance is not negative. So the absolute value of this thing would be 5. So going back up to here, find the absolute value of each complex number, it's going to basically be if this is a and bi, right, it's the square root of a squared plus b squared is the distance. And that's the distance formula. So for this one, it's going to be the square root of 7 squared plus -1 squared. That's our distance. So it's the square root of 49 plus 1. So square root of 50 is our d. We can simplify this a little bit, and we can say that d, or the absolute value, whichever, is 5 root 2. So that's how you do those. It's just basically a glorified Pythagorean theorem. Okay, and next, identify each complex number graphed. Let's just look at number 19. So this is the point 1, 3. So that translates into the complex number 1 plus 3i. Well, it's pretty easy too. Okay, so that's everything from the packet, and I will have another video for you with everything from the other packet.